I'm going to talk about testing the significance of independent variables. And this follows from simple linear regression, where you made a hypothesis test for the slope. The only difference now is that there are multiple tests for each one of those slopes. We have the null hypothesis, which is that the slope of that variable, whatever it is, let's say it's j, is equal to 0, versus the alternative that that slope is not equal to 0. Okay? So remember, when the slope of a variable is equal to 0, that means there is no relationship with the variable and y. So that means that for every level of x, y stays on average the same. So the null hypothesis is that the slope is 0, meaning there's no relationship, linear relationship between the variable j and y, versus the alternative that there is a relationship. Now we have to take into account that this is in the presence of the rest of the predictors. So what that means is that, for instance, we have h here, and we can see that h, the hypothesis test, again, is the null hypothesis is that the slope for h is equal to 0, meaning that there's no relationship between h and the price of a clock. The alternative is that h, the slope of h, is not equal to 0, meaning there is a relationship. We get a test statistic. First of all, we get an estimate of 12, and we get a standard error of 0.9. Now remember, these standard errors might be inflated if there is multicollinearity. In this case, we found previously that age and number of beaters are not correlated, so we can assume that these standard errors are not inflated. We also took a look at the variance inflation factors, and basically we found, if I can point out that here, that the variance inflation factors of these two variables are about 1. So they are inflated by a factor of 1, which means that they're basically not inflated at all. So we can, what we know is that these variables don't have any collinearity among them. So they are not collinear. The test statistic, then, we can trust it. The test statistic is going to be the slope that we got for h divided by the standard, the estimate of the slope, divided by the standard error of that slope. And we can see that that's 12.74 over 0.9, which gets you 14 standard errors, which means that the slope is 14 standard errors away from 0. If we look at in terms of probability, what are the chances that we get a t-statistic as high as that or higher, given that the null hypothesis, and this is an important part, that the null hypothesis here is true, and we get a 0%. It's basically not possible. So, in other words, there is a relationship between age and price, but the point here is that this is in the presence of the number of bidders. We don't know how these variables are going to be related individually with price, but we know that in the presence of the other variable, these are related. It might be that these these p-values behave completely different. And the cases where they behave different is when there is correlationship or collinearity between these two variables. And again, the reasoning is because the standard errors are inflated. Okay, so we can always get a confidence interval on a parameter estimate on a slope by using the t-statistic and multiplying that by the standard error of the slope using n minus k plus 1 degrees of freedom on the t-statistic. And you can get that using the confidence function in R. You can get different levels, in this case 95% confidence interval, and here's 99%. I wanted to go a little bit of what that means really. So what does it mean that a confidence interval, let's say for the variable age, what does it mean that the confidence interval on the slope, that we are 95% confident that the slope is between 10.89 and 14.59? Does it mean that that the slope is going to be there 95% of the time? And the answer is not. That's not what it means. Because the true slope, beta of age, doesn't change. That is the true slope of the relationship between price and age of the clock. So let's think, let me give you an idea. If that true slope is 11, meaning that as age of the clock increases by 1 year, then on average the price increases by $11. That slope will remain constant. That doesn't change. That is the true value. The confidence interval basically means that if we actually did make multiple samples, and again, remember this regression is based on a sample of 32 observations. So if we made, let's say, a sample here of 32, in that sample we will capture the true one. Another sample here, another sample here, and so on. But 5% of the samples that we can get, 5% of them when we construct the confidence interval, that confidence interval will not contain the true slope. So sometimes when we think about confidence intervals, we are thinking that what is changing is the slope or that parameter, and in fact that doesn't change. That is set. What changes is that if you were able to take multiple samples of the same sample size, then 5% of those samples will produce a confidence interval that doesn't contain the true slope. All right. Confidence intervals and prediction intervals, for when we make predictions, the point of this is that for a particular value of x, the values of x for each independent variable, it is unlikely that the value will equal the mean value of y, or the parameter estimate. So we use sometimes confidence interval to quantify the amount of error. So in other words, there are two types of confidence intervals that we can make. Confidence intervals on the average and prediction intervals on individuals. We've talked about this a little bit, but I wanted to talk to you a little further on the concept of distance value. And let's suppose that you have two variables, let's say x and y here, whatever those variables are. The distance value is basically taking in consideration the variable x. If we are closer to the mean of x, then we would expect that prediction to be more accurate, because it is closer to the average of the points, where the bulk of the points of x, the variable x, is. So basically what the distance value tells you is, as you get away from that mean of x, so let's say this is x bar here, if you go above of that or very below, then that distance value gets larger and larger, and it gets larger and larger by to the power of 2 is squared. This is divided by s of xx, which is the same thing in matrix notation as x transpose x inverse. And the idea is that if we make a confidence interval, the further away we are from the value of x bar, from the mean of the variables, the predictor variables, then the more difficult it is to make a prediction. So that's why you will see that confidence intervals on the average, which is this here, you can see this actual lines that are closer to the average. Remember, this is what we are doing when we're getting a confidence interval on the mean. It's just the confidence interval on the average value of y for a given x. As we get further and further away from the mean, then those become larger. Those confidence intervals become larger and larger because they are somehow accounting for this distance value. For individuals, it happens the same way. I mean, the confidence intervals gets larger and larger the further away you are from the mean of x. So in multivariate, multiple linear regression, the same thing happens now. But the idea is that we have different values of x. So we have to compute the mean of every single predictor variable. And the further away we are from that mean, the more difficult the prediction is. So that's why you will see that when you do a confidence interval for a mean value, this confidence interval is obtained by getting the prediction value plus or minus what we call the margin of error. And the margin of error is based on the t statistic with n minus k plus 1 degrees of freedom, but is multiplying that by the standard error of the estimate. The standard error of the estimate is basically just our MSE, this S is here, our MSE, multiplied by the square root of the distance value. All right. So remember that this is what we sort of similar to what we got in the X transpose X matrix when we got the standard errors of the parameter estimates. The only difference is that the distance value is calculated by also considering the number of observations. So that's what goes on the background. And that is the reason why the higher the distance value, the larger the confidence interval on the mean. And that's what you can see here. The further away you are from that mean, then the larger the confidence interval on the average. Remember that you can get this using the predict function in R. Now, I wanted to point out if you have to make a prediction in R and now you have more than one variables, you still have to use the data frame function, but put the values of each variable separated by a comma. Remember that the interval equal to confidence gets you a confidence interval on the mean value of y, or the average. So that is basically the confidence interval on the average. Now the prediction interval is the same formula. I mean, you get the prediction here, the t statistic, the standard error of the prediction, but the standard error is multiplying our MSE times the square root of 1 plus distance value. So what happens is that we have to add an additional RMSE. I mean, we have to just multiply that RMSE by 1. So even making the amount of error larger because we are accounting for an individual and not the average. So that's the reason why this is larger, because we are multiplying RMSE here by 1 and then RMSE by the distance value. So it's two things added together. An additional RMSE for the individual and an RMSE for the average. So in terms of code, you use the predict function and put the variables in a data frame, but you use the interval equal to predict or prediction. Remember, you can also change the level by adding level is equal to whatever level you want, let's say 99, but by default, this does the 95% confidence interval. All right, so the idea on this is that now you are able to compute confidence intervals on the both the average and also the prediction intervals on individuals.